Good morning, afternoon, and evening, everyone. This is Hao Wang from Shanghai Tech University. Thanks for the invitation from IEEE PELS and Tech. I'm very glad to have this platform to share with you about my thoughts regarding the conductive charging of electrified vehicles. And also, I'm going to share with you some of our recent research work. First, please let me briefly introduce about my university. Shanghai Tech is founded by Shanghai Municipal Government and the Chinese Academy of Sciences. It is a young university founded in 2013, and we began to recruit the first batch of undergraduate students in 2014. So Shanghai Tech is a small-scale and university has high faculty and student ratio. It is located in the Zhangjiang High-Tech Zone in Shanghai, where we are constructing the first national science center in China. In Shanghai Tech, we have the Center for Intelligent Power and Energy Systems. Right now, we have 5 faculty members, very international. The faculties are coming from Virginia Tech, Georgia Tech, University of Maryland, Hong Kong University of Science and Technology, Hong Kong City University. The lab space counts 500 square meters. The research in SIPs include power electronics, power systems protection, wireless power transfer, energy harvesting and IoT, and GaN power devices. Here is my lab, Power Electronics and Renewable Energies Lab, which we call it PERL at Shanghai Tech. My lab was opened in 2014 September. At that time, I just got my PhD degree from University of Maryland and returned to China. In PERL, we have 100 square meter lab space, 4.5 million Chinese yuan facilities, 7 PhD students, and 1 master student. We have already graduated 10 alumni. Here is the outline of my presentation. It includes 5 parts. In the first part, I'm going to talk about the trend of transportation electrification. As we know, plug-in electrical vehicles include electrical vehicles and hybrid plug-in electrical vehicles. So actually, the electrical vehicles was not a new thing. It was invented in 1834, and at the turn of 20th century, EV counted for 38% of the US vehicles. However, after 1930, the electrical vehicles almost vanished. The main reason is because there was a lack of mature energy storage technology, and also power electronics haven't been invented at that time. But now, the Li-ion power battery technologies is getting mature, and although the battery counts for a large part of the EV cost, the battery price is keeping going down, so which also bring the going down of the electrical vehicle price and make it more affordable. So we commonly believe that $150 per kilowatt is the turning point for massive promotion of electrical vehicles. And on the other hand, the power electronics technology is the enabler of high performance plug-in electrical vehicles. And we are seeing that the power electronics converters are becoming more efficient, more compact, more reliable, and less costly. So based on this, we are embracing the rising of the electrical vehicles in the new era. According to the prediction from the Bloomberg, the sales of electrical vehicles is going to rising up very quickly, and it is expected the sales of EV is going to count 54% of the total sales of vehicles. And also over the past year, we have some big things happening. So in 2019, the Tesla Gigafactory start from groundbreaking to ready for production of electrical vehicles as Model 3. So actually now we can see lots of made in China Model 3 driving on the road in Shanghai. And also this month, the Tesla becomes the most valuable automaker of all over the world for the first time. And last month, the Chinese government released the new infrastructure 2020 national strategy. So electrical vehicle charging station is one of the 7 new infrastructures which is going to be massively deployed in the mainland China. And power electronics is playing a very important role in the progress of transportation electrification. Typically, we call it the enabler of transportation electrification. So as shown in the figure to the left, the red blocks indicate power electronics modules. We can see that there are lots of power electronics modules in the vehicle. However, there is a lack of charging infrastructure, which causes the range anxiety problem of the ordinary consumers, which is the major barrier from driving electric. And that's why we have today's talk, right? So next, I'm going to share with you about the challenges and the trends in PEV conductive charging. So as you may already know, the charging power levels can be divided into 3 categories. So level 1 charging is below 3.3 kilowatt. It can be accomplished at home or office, and it doesn't require specific EVSE. Level 2 charging has the power range between 3.3 kilowatt to 20 kilowatt. So usually it can be finished in the private or public outlets, and it requires specific EVSE. Level 3 charging is most powerful, and it has the power level between 50 kilowatt to 100 kilowatt. We can finish the charging within 1 hour, and it requires specific offline charging station. Now let's look at the charging profile of Li-ion battery. So as the figure in the middle shows, the Li-ion battery charging includes 4 stages: pre-charging stage, constant current charging stage, constant voltage charging stage, and recharge. And for some applications, we might have the 5th charging station, which is constant power charging station, charging stage. So the battery voltage varies with the change of battery state of charge, so which mirrors the SOC to a wide battery voltage range. So therefore, the battery charger needs to be adapted to an ultra-wide battery voltage range, so which we can use it to charge the deeply depleted battery pack. And also, as the table in the right shows, the current commercialized DC fast chargers also are adapted to the ultra-wide output range from 50 to 500 volt to 150 volt to 920 volt in order to be adapted to different vehicle types, such as passenger cars and also heavy-duty vehicles. So the charging of electrical vehicles includes the onboard charging and off-board charging. So although the wireless power transfer is a hot topic, we still have the conductive charging as the dominant charging technology. So that's why we focus on conductive charging in this talk. And also, the charger requires galvanic isolation. So the figure to the right indicates 2 types of isolation. So here is the great frequency isolation, and here is a high frequency isolation. So among them, the high frequency transformer has the advantage of compact size and high power density, so it's preferred here. And the battery charger typically include 2 stages, right, as shown in those 4 figures. One stage is AC-DC stage, and also to realize the power factor correction. And the second stage is the DC-DC stage, which is the battery interface. So as shown in those figures, we can see that the DC-DC converter is the key interface between the vehicle and the grid, and which need to be adapted to the battery terminal voltage. So that's why we focus on DC-DC part in this talk. So recently, the US Department of Energy released the US Drive 2020 and the 2025 target, in which they provide very detailed targets to the cost, specific power density, and the efficiency of the onboard DC-DC converter and onboard chargers. So also, the future vehicle need to be adapted to the vehicle-to-grid technology, which require the battery charger to be enabled to achieve bidirectional power flow. So to achieve those targets, in the perspective of power electronics, we need to explore innovative circuit topologies, integrated architectures, advanced modulation and control strategies, and application of wide bandgap devices, and also the high-frequency magnetics integration. So therefore, we have a lot of research opportunities to explore in power electronics. So next, let's look at the current DC-DC conversion solutions. So the mainstream DC-DC topology, which is adapted to the EV charging, include phase shift full bridge converter and the LLC multi-resonant converter, as shown in the figure on the top. The table on the table below lists the comparison between those two topologies. As shown, the LLC resonant topology has the advantage of full range ZVS, secondary side diode ZCS turning off, low voltage stress, small magnetic size, and high efficiency. So it is overall better than the phase shift full bridge topology. Therefore, in this talk, we will focus on the LLC and its derivative resonant topologies. So next, let's have a look at the basic operation principle of the frequency modulated LLC converter. So as shown in the figure to the left, so the left primary side is a full bridge inverter which generates a 50% square wave. The secondary side is a diode bridge rectifier. So we can change the frequency of the square wave to modulate the output. For the LLC converter, we can use the first harmonic approximation method to model it. So its model is as shown in the figure to the top right. According to this model, we can derive the voltage gain expression and plot the voltage gain curves as shown in the figure down to the right. So as indicated here, when the resonant tank is operating in the inductive region as the shaded part, we can realize the ZVS turning on of the primary side MOSFETs. For the LLC converter, there is a very classic dilemma: how to realize the output wide output range and the narrow frequency band simultaneously. So as we know, when the switching frequency is below the resonant frequency, there will be large redundant circulating current, which will incur large voltage stress. And moreover, the low frequency require bulky transformer, which degrade the power density. On the other hand, when the switching frequency is higher than the resonant frequency, the secondary side diodes will have large di over dt in turning off. And moreover, the large turning off current for MOSFET will also incur high switching losses. And the high switching frequency will also incur high core loss. So moreover, the when the switching frequency derives from the random frequency, the first harmonic approximation method will lose its modeling accuracy. Besides, it's very difficult for ALC converter to realize the back function. And in the light load condition, due to the existence of the parasitic capacitance of the diode and the transformer, the voltage even increase with the increase of the switching frequency, which will cause problem to the frequency modulation. Therefore, we can say that the ALC topology is unfavorable for wide output applications. So therefore, we have a very classic problem to solve: how to realize wide output range plus narrow frequency band. And also that's the main focus of today's talk. According to our survey, there are some state-of-the-art solutions which we'll give a brief summary here. So the first type will be the phase shift ALC converter. So we can introduce the phase shift between those two half bridges to realize the back function of the ALC converter. So for the high output voltage applications, we still use the frequency modulation. So the efficiency is similar to that of the ALC converter. And also, we can use this phase shift to constrain the inrush current during the start-up process and also the short circuit condition. However, the phase shift ALC converter also have some problems. At light load, if the phase shift angle is large, as shown in the figure to the left, there will be a large freewheeling time. So therefore, the primary side resonant current is going to drop to a very low number, a very low value. So this will incur the ZVS failure of the lagging lag MOSFETs. And in heavy load condition, if the phase shift angle is large, as shown in the figure to the right, in the TE region, S-force current will switch to its body diode. So at the end of TE region, S3 is on. So the S-force body diode will be forced to turn off. This will incur reverse recovery problems and also incur voltage draining in the switch S4. So also the lagging lag will lose ZVS. So this will incur the thermal issues with the primary side MOSFET. The second solution is use the boost mode ALC, which we introduce two active switches on the secondary side. So we utilize pulse frequency modulation to regulate the low output voltage. For the high output voltage scenario, we utilize the power frequency modulation plus secondary side phase shift modulation. So the advantage of using this boost mode is that we can first squeeze the frequency range, and second, we can easily realize the magnetic design, and thirdly, we can achieve high efficiency in the low output voltage scenarios. In the T1 region, the secondary side switch are both on, so the transformer is short circuit, and therefore the energy is stored in the resonant tank, and later on it is released to realize the boost function. However, in deep boost mode, which will require a long T1 time, this will bring a smaller magnetizing current, which will make it very difficult for the primary side switch to realize ZVS turning on. And also the secondary side switch is turned off at large current. So this will bring large turning off losses. And moreover, the control is rather complicated. So the third solution is the full and half-bridge switch of the full-bridge ALC converter. So here shows its operating principles and features. So basically, we can, if we want to achieve a lower voltage range, we switch the primary side full bridge to a half bridge as indicated in the figure to the right. So we can reduce the root mean square voltage of VAB by half. So therefore, the output voltage range can be extended, and also we can effectively squeeze the frequency range. However, the half-bridge, full-bridge switch will bring harsh modal transition, and also in low-voltage, high-current scenarios, the current stress of the half-bridge will increase. This will bring the thermal management issue for the half-bridge. So to improve, here is a enhanced version of half full bridge switch. It is based on a T-lag as shown here. So when the bidirectional switch here is on, so the primary side switch network will be configured as a full bridge with 2 capacitors and 1 active switch bridge. So we can also realize the similar target with squeezed switching frequency range, better tuned resonant tank, improved efficiency over the wide range. And moreover, the voltage stress in this mode is reduced by half. However, it also have the similar issues with the previous version, like the transition process and the thermal issues on the primary side. And moreover, it also has increased components count and power losses. So the next solution is T-lag ALC with fixed frequency pulse width modulation control. We can use it to expand the voltage range. So as shown in the schematic, we have switch Q5 and Q6 as high frequency switch. So by configuring the switch pattern of this switch network, we can realize a full level VAB, which is fed to the resonant tank, right? The height is V in 0.5 V in minus V in and minus 0.5 V in. And we can modulate the D to modulate the ratio of the V in level. So therefore, we can modulate the effective RMS voltage of VAB to regulate the output voltage. And one advantage of this solution is that its voltage gain is weakly dependent on the load condition, as shown in this figure. And moreover, the magnetizing inductance has little impact on the voltage gain performance. Therefore, it can be used to constrain the large circulating current. Next solution is the interleaved ALC with pulse frequency modulation plus phase shift modulation. So which we use 2 full bridges on the primary side and 2 separate resonant tanks. On the secondary side, we use 3 diode bridges. So to realize the boost function, so we have the phase shift equals to pi. So the secondary side is equivalent to series connection. It's similar to the conventional ALC converter, which adopts frequency modulation. And when we want to buck the voltage, we introduce the phase shift modulation. So we decrease the phi. Then the interleaving effect will help to buck the voltage gain. And in the extreme condition, if the phi equals to 0, the secondary side is equivalent to parallel connection. So the voltage gain will be equals to 1. So we can achieve 1 to 2 voltage conversion range in the phase shift mode to extend the voltage gain range. And next one is the 3-level ALC converter with PWAM control. So which we operate the converter in fixed frequency Fs equals to random frequency, and we introduce the PWM and phase shift to regulate the equivalent input voltage VAB to the resonant tank. So different switch pattern correspond to different shape of this VAB voltage as shown in the circled part in the bottom figure. So we can regulate the output voltage. And one more advantage for this solution is that it can also realize bidirectional power flow. So we have talked a lot about the state-of-the-art works. Next, we are going to introduce some of our research work in the PERL at Shanghai Tech. So the first project we did is the maximum efficiency point tracking technique of ALC converter. So it is inspired by the ALC converter operating at the resonant frequency. So when Fr equals to Fs, the normalized voltage gain equals to unity. So at this point, we have the minimized redundant circulating current. We have the secondary side diodes turning off with low DIDT, and also the overall current stresses are minimized, so which are all our favorite features. So inspired by this, we proposed the maximum efficiency point tracking technique. So instead of constant DC link voltage here, we adopt the variable DC link voltage to actively track the battery pack voltage. Therefore, we can effectively narrow down the frequency band and make sure that the switching frequency is always very, very close to the resonant frequency, as shown in this region. So therefore, we can declare that the ALC topology is always operating at its optimum operating point. Besides, we can also have less requirements on the back function of ALC. Therefore, we can adopt a large inductance ratio. So large LM means that we can use a large magnetizing inductance, which help us to further reduce the circulating current. However, the variable DC link voltage will also bring new challenges to the front stage, AC to DC power factor correction stage. To realize a ultra-wide DC bus voltage range, the conventional boost topology will no longer be suitable here. To resolve this issue, we propose to use SAPIC power factor correction solution, which we use DCM plus two-phase interleaved plus coupled inductor to optimize the performance. So utilizing the combination here, we can reduce the input current ripple and also reduce the output voltage ripple and the total harmonic distortion. Moreover, we can realize the zero voltage switching of MOSFETs and the zero current switching of diode. So the figure on the top 3 shows the experimental results of the ALC converter. So as shown, in heavy load, 420 volt, and light load, 100 volt output, the ALC converter is always operating at its resonant frequency, which brings the optimum operating condition. And also we make the comparison of efficiency, as we can see that compared with the conventional constant DC bus solution, the variable DC bus solution can achieve the efficiency increase of the converter over the wide state of charge range. And the bottom 3 figures shows the experimental results of the SAPIC PFC converter. So as shown in the scale of the switching frequency, so we can see that the experimental waveform are identical to the theoretical analysis. And in the scale of great period, so we can see that a very good power factor correction is achieved. And this figure shows the interleaving effect, as shown that the interleaving effect effectively decrease the current ripple and also the total harmonic distortion. Okay, the second project is secondary side pulse width modulated LLC converter. So here it shows the basic operating principles. So the schematic is shown in the figure to the top left. So as we can see that the primary side is identical to the conventional full bridge LLC converter. And on the secondary side, we have 3 diodes and 1 active MOSFET. So the figure to the right shows its steady state simulation waveform. So the converter is always operating at the random frequency. The primary side generates a 50% duty cycle square wave. Its output voltage regulation is achieved by regulating the duty cycle of the secondary side switch S5. So here is the driving signal of S5. So we introduce a phase shift between the VGS2 and the VGS5 to realize the zero voltage switching of S5. So here is a minor delay here. When the duty cycle of VGS5 is below 1, so the second side is like a voltage Doppler rectifier circuit. When the duty cycle is below 0.5, the current all flows through the body diode of S5. It's hard to achieve the charge balance of the capacitor CO1. So therefore, the duty cycle should be constrained within the range of 0.5 to 1. And for this converter, all the MOSFET can realize zero voltage switching turning on, and all the diodes can achieve their current switching turning off. So this slide shows the voltage gain behavior. So the 3 figures correspond to the voltage of CO1, CO2, and the output versus the duty ratio. So as shown in the left figure, the capacitor CO1's terminal voltage is well constrained by the duty ratio. And the capacitor CO2's terminal voltage is not sensitive to the duty ratio and load condition. It is almost constantly equals to 1. And when D approaches to 0.5, the terminal voltage of VCO1 approaches to 0. So which incurs the overall output voltage approach to 1. And when D approaches to unity, so it's equivalent to a voltage doubler circuit. So the CO1, CO2 both have their terminal voltage equals to 1. And the total output voltage will be equals to 2. So therefore, we can regulate the duty cycle of this S5 to realize the voltage regulation of the output. And also, according to this figure, we can see that the voltage regulation performance is not sensitive to the load changes, which is good here. To make a performance comparison, we designed 2 prototypes. One is based on the proposed PWM LLC, and one is based on the conventional LLC. So as shown that they have similar parameters, only the magnetizing inductance and the transformer are different. So as can be seen here, the conventional LLC has larger LM and bigger magnetic core. So the figure to the right shows the digital control scheme of the proposed converter. So as we can see that primary side is an open loop operation. So it generates a 50% square wave, right? And secondary side sample the charging voltage and the charging current and feed it back to the microcontroller. Microcontroller estimate the state of charge and choose the charging mode. So in constant current charging mode, we only require a current feedback loop. In constant voltage charging mode, we require to have a double loop, current loop and the voltage loop to realize the closed loop control. So this page shows the comparison with the conventional LLC converter. So the figure on the top shows the simulated parameters of PWM LLC and the PFM LLC with different output voltages. So as shown that compared with the conventional frequency modulated LLC converter, the proposed PWM LLC converter have obviously lower current stress on the primary side, and also its delta B is almost constant, right, due to the fixed frequency operation. However, the conventional LLC will have a big variation range of the delta B. Okay, so the figure to the right shows the power loss analysis of those two different prototypes. So as shown that the low primary side RMS current makes that the primary side MOSFET conduction loss of the proposed converter much smaller than the conventional LLC converter. And figure to the bottom right shows the comparison of the size. Although in the proposed converter we have additional S5 and D3, which increased the size of active devices, but the delta B is obviously smaller, so we can use a much smaller transformer, which helps to reduce the size of the system. And moreover, the parameter design is simpler. So generally, the proposed converter has lower primary side conduction losses and a better power density performance. So here is the experimental results. The left two figures shows the soft switching of the primary side MOSFETs. And middle two figures show the S5 it has zero voltage turning on, and also secondary side diodes has zero voltage turning off, zero current turning off. And the figure to the top right shows the dynamic response of the designed prototype when the load steps from 300 ohm to 100 ohm. So we can see that the designed converter has a good dynamic response. And bottom right figure shows the efficiency data. So we can see that the proposed converter has good efficiency performance over the wide output voltage range. And here is the third project to resolve the issue of conventional LLC converter in ultra wide voltage gain range. So we proposed a H5 bridge based asymmetric LLC random converter. By configuring the on-off state of the S1 to S3, so make them either normally on or normally off, so we can configure the inputs of those two random tanks, VAB and VBC, as either full bridge, half bridge, or even idle state. So the table here shows the 6 modes input voltage of the random tank. So the 6 modes can operate independently. By introducing 2 asymmetric transformer and random tank, we can realize 6 output voltage segments. However, there is a mismatch issue for this asymmetric resonant tank. To analyze its impact, we utilize the very classic first harmonic approximation method to obtain its general equivalent circuit model here. In model 1 and model 2, we can easily equivalent it to a single circuit model here, so which we can use the conventional method to solve the voltage gain expression. And in models 3 to 6, we cannot just equal them, so we need to split the load side by finding out two points D and E which have the same voltage potential. So and then we short D and E, so we can split the circuit to achieve two resonant tank model. So utilizing this circuit model, we can analyze the voltage gain expression and plot the voltage gain waveform. So therefore, by reconfiguring the inputs of the two resonant tank, we can effectively extend the voltage gain of the LC converter. So basically, G1, G2, G3 to G6 indicates the voltage gain in these 6 modes at the resonant frequency. And also, according to FHA method and the model we constructed, we can derive the voltage gain expression and plot the gain waveform. So the shaded region indicates the operating region. So as can be shown here, by switching the adjacent operating modes, we can be adapted to different voltage gain ranges. Therefore, we can achieve the target of narrow frequency band and wider voltage gain range. Correspondingly, we can also get the advantage of low current stress. So here we make a comparison of the conventional wide gain range LC converter and the proposed reconfigurable converter. So as we can see, the proposed topology can effectively reduce the current stress. Meanwhile, the ZVS performance can also be strengthened. So as shown in the figure in the middle, so we can for the proposed converter in model 6, we can utilize a smaller deadband time to realize the ZVS. So this can help us to effectively increase the effective duty ratio. And moreover, we can easily achieve the model transition without any harsh model transition issues. So generally, we can well realize the LC converter's soft switching feature and also reduce the current stress to improve the performance of the LC converter over the wide voltage range. So here shows the experimental results. The measured efficiency data of the designed prototype within the 6 operation mode, model 1 to model 6. So we can see that we can realize a ultra-wide output range from 85 volt to 450 volt, and the peak efficiency reaches 97.05%. And even at the 85 volt output voltage, we can realize efficiency above 90%. The project 4 is the phase shift modulated interleaved LLC converter. So we introduced two matched transformer. And on the primary side of those two transformers, we utilize two matched resonant tank and two half-bridge inverters. So to parallel them to the input voltage source. On the secondary side, we put them in series connection and connect to a shared full bridge diode rectifier. So for this converter, it's always operating in the random frequency. By controlling the phase shift between those two half bridges, we can realize a ultra-wide output voltage range, and meanwhile we can achieve the soft switching of all the power devices. So the figure to the right shows the critical steady-state waveform of the proposed converter. So as we can see that we can control the phase shift between the VGS1 and the VGS3 to regulate the output voltage. And the VAB1 and the VAB2 represents the input voltage of those two separate resonant tanks. And the VSAC and ISAC represent the transformer secondary side voltage and currents. By introducing the equivalent inductor current ILR prime, ILR double prime, and the equivalent capacitor voltage VCR prime and VCR double prime, so we can couple the two transformer into a unified model, or decouple them into two equivalent models. So therefore, we can simplify the analysis progress. So the figure in the middle shows the equivalent input voltage of the resonant tank and equivalent voltage of the across the magnetizing inductor. So based on them, we can obtain the current and the voltage information of each resonant tank, and we plot it here into a trajectory plot. So here is the trajectory for the inductor current and the capacitor voltage for those two resonant tanks. So as shown that all the MOSFET can realize ZVS. However, the S1 and the S2 has lower turning on negative currents, which means that they will be more easily to lose ZVS. Therefore, the realize of ZVS is mainly determined by the S1 and S2. By introducing the equivalent inductor current and the equivalent capacitor voltage concepts, we can obtain the information of resonant tank voltage and current, and accordingly we can solve the voltage gain by solving the nonlinear equilibrium groups. The figure on the left shows the relationship between the voltage gain and phase shift angle under different load conditions. So by controlling the phase shift, we can easily realize the ultra-wide output range from 0 to 1, right? Very low voltage to 0 volt. And the figure to the right, the two figures on the right, shows the S1's turning on negative current. We know that to achieve ZVS, we need to have a negative current to discharge the COSS of the switch to realize the 0 voltage condition. So we also make the comparison with the conventional phase shift LC converter, as can be seen here. Compared with the conventional phase shift LC converter, our designed converter can realize a full range ZVS, and also its negative current is evenly distributed over the wide phase regulation range. And here shows the selection of the inductance ratio Ln, right? So here we choose the Ln equals to 12, which can ensure the 0 voltage switching with enough negative current, and also we have a large Lm, so which help us to suppress the circulating current and its power losses. So based on this concept, we designed a prototype. The input voltage is 390 volt, and output voltage range is from 10 volt to 420 volt. So it is constantly operating at the random frequency. So the right figure shows the control diagram. So the sensor senses output voltage and feedback to the microcontroller through a PI regulator to regulate the phase shift between the primary side two switches. Then we can realize the closed loop regulation of the output voltage. Here is the experimental results of the design prototype. The figure to the left shows the steady-state waveform with the highest output voltage and the peak power. So we can see that the two run tanks are fully symmetrical. It is identical to the operation of the conventional ALC converter. And the middle two figures show the experimental results of the 100 watt and the 100 watt. So low voltage and light load. So we can see that there is a minor phase shift between the primary side two half bridges. As can be seen that even with the small phase shift, we can realize the zero voltage switching of the primary side MOSFET. So this proves that the proposed topology has very wide ZVS range. And figure to the right shows the dynamic response of the designed prototype. So here is the output voltage step change, and here is the output the load resistance step change. So we can see that the designed prototype can realize a good dynamic response. So the fifth project is based on a reconfigurable transformer and a reconfigurable primary side bridge. So here is the schematic of the proposed topology. The main concept is that we introduce two 4-quadrant switches and one 3-winding transformer with center tap here. So therefore, on the secondary side, by configuring the switch pattern of S5 and S6, we can realize 3 effective turns ratios of the transformer. And to further reduce the voltage gain range in the lowest output voltage scenario, we configure the primary side to a half bridge. So therefore, we can achieve 4 operation modes. So here is the primary bridge structure and the transformer turns ratio of those 3 operation modes. Mode 1 has the lowest voltage range. So basically, the output voltage can be divided into 4 segments. So in those 4 operation modes, according to our designed parameters, we can use first harmonic approximation method to calculate the voltage gain of each operation mode. And the figure to the right shows the voltage gain versus switching frequency in different operation mode. So there are 4 segments over the entire output voltage range. So in each operation mode, the design of the resonant network parameters is less constrained by the voltage gain requirement, which is good for us. Meanwhile, we can also ensure that the switching frequency will be close to the resonant frequency to optimize the circuit operation, and also which guarantees the modeling accuracy of FHA. And moreover, we can easily realize the soft switching over a wide range. It should be noted that for this proposed structure, the half bridge is only enabled in the lowest output voltage range. So basically, for the same output voltage level, low output voltage represent light load. And light load and half bridge mode can effectively reduce the transformer ion loss. So therefore, the light load efficiency can also be improved due to the introduce of the half bridge in this segment. So one of the key thing here is how to design the transformer. So basically, the transformer design is based on minimizing the total loss of the transformer at the random frequency. So we can construct the loss model of the transformer under the constraints of avoiding the magnetic saturation. We can choose the global minimized loss point to design the transformer. So we can calculate the turns number on secondary side. So according to the required parameters, we can tune the air gap and the coupling coefficients of the transformer to realize the optimized design of the transformer. In order to validate the proposed concept, we designed a 4 amp rated prototype to realize power conversion from 390 watt to 60 to 450 ultra-wide output range. So the table on the left shows the experimental parameters and device selection. The figure on the right shows the measured efficiency in different output current, 1 amp, 2 amp, 3 amp, and 4 amp. So as shown in the experimental results, the designed prototype can realize ultra-wide output range from 60 watt to 450 watt, and the peak efficiency is 97.5%, and the global efficiency is always above 90%, which is impressive. To compare, we also designed a prototype using the conventional pulse frequency modulation LC converter. So the measured efficiency of the comparison prototype counterpart is shown in the dashed black line here, and here. So we can see that the conventional LC converter cannot realize such a ultra-wide output voltage range. Actually, when the output voltage goes down below to 250, the switching frequency already reach 350 kilohertz. And the buck effect is very poor, so it's hard to further decrease the output voltage by increasing the frequency. And also, although for some segments the conventional LC exhibit better efficiency, the proposed converter exhibit a overall better efficiency and better global efficiency. Correspondingly, we did the model transition experiments. So figure A, B, and C shows the transition from 1 to 2, 2 to 3, and 3 to 4, when the output current equals to 1 amp, 2 amp, and 1 amp. So as shown in the figure A, so when the mode transition from 1 to 2, the primary side is reconfigured from half bridge to full bridge, and the switching frequency jumps from the lower bound in mode 1 to the upper bound of mode 2. So there is no overshoot in the transition process, right? And figure B and C shows transition from 2 to 3 and 3 to 4. We just reconfigure the 4-quadrant switch to change the effective turns ratio of the transformer, and also the switching frequency jumps from the lower bound of the previous mode to the next to the upper bound of the next mode. Also, there is no overshoot problems, so we can see that we can achieve a smooth mode transition. And figure D here shows the dynamic response when the output steps from 450 watt to 250 watt. So we can see that a very good dynamic response is achieved. No overshoot is incurred. So finally, let's look at the bidirectional power conversion, which is adapted to the vehicle-to-grid technology. And also, I'd like to introduce you about one project we did in this specific area. So similar to the unidirectional DC-DC converter, the the mainstream bidirectional DC topology also has two categories. First one is CLLC resonant bidirectional converter. Second type is dual active bridge topology. So in comparison with the CLLC resonant solution, the dual active bridge has the advantage of fixed frequency and phase shift modulation. Also, it has lower components counts. And also, it requires only one inductor and one transformer, lower passive components count. Although CLC can realize the full range ZVS and ZCS, it also requires the synchronized rectification of the secondary side, which is complicated. But DAB can avoid this synchronized rectification. And also, since for DAB we do not require the magnetizing inductance, so we don't need to open air gap to the transformer, which is good to massive production. So let's have a review about the conventional DAB topology. So it is composed by two half bridge, two full bridges back to back, right? And M is the normalized voltage gain of DAB converter. So conventionally we use single phase shift modulation to regulate the DAB converter. So the primary side voltage VAB and the secondary side VCD are both square wave with 50% duty ratio. We can regulate the phase shift between those two square waves to regulate the delivered power. However, if we compare the transformer voltage and current waveforms with voltage gain equals to 1 and the voltage gain equals 0.5, we can see that when the transformer terminal voltage are mismatched, the current stress of transformer will increase. Obviously, this will incur very large current stress to the circuit components and also degrade the conversion efficiency. Therefore, we can say that the conventional single-phase shift is no longer suitable for the wide output range applications. To improve, we propose a hybrid bridge configuration based on DAB. So on the primary side, we introduce the CP, which is the DC blocking capacitor, so which realize the hybrid bridge structure. So the figure to the right shows that when the normalized voltage gain M equals to 1, the driving signal, and when M equals to 0.5, the driving signal. So we can see that by changing the driving signal of S4 and S3, we can configure the hybrid bridge to be either in full bridge mode or half bridge mode. So therefore, we can achieve the match of the transformer voltage in those two special cases. So however, this hybrid bridge configuration is only suitable for special cases of M equals to 1 and M equals to 0.5. So furthermore, to realize the transformer voltage match between M equals to 0.1 and M equals to 1, we propose the hybrid modulation scheme. So we operate the primary side full bridge in an asymmetrical duty cycle regulation, so as shown here. And S4's duty ratio is bigger than 50%. So the additional part here is defined as duty ratio D. And S3 and S4 are complementary with certain deadband. So meanwhile, the primary side bridge output voltage becomes 3-level voltage, right here, 3-level. So therefore, the DC blocking capacitor is also regulated by the asymmetrical duty cycle. And the transformer primary side voltage VAB is determined by the input voltage VOP and the DC blocking capacitor. Therefore, by regulating the DC blocking capacitor's voltage, we can realize the match between the transformer voltages VAB and VCD. So therefore, we can utilize the asymmetrical PWM to track the variation of the primary side voltage to always realize the match of the transformer voltages. So we designed a prototype to validate our concept. The design parameter is here. The input voltage is, the primary side voltage is 100 volt to 200 volt, and the secondary side voltage is 300 volt. And based on those parameters, we can obtain the curve of RMS inductor current versus the output power with different output power. And also we made the comparison of the proposed hybrid modulation and the conventional single phase shift modulation. So we can see that the proposed modulation technique has much smaller root mean square voltage, root mean square current under the same power level. This means that the circulating power is reduced obviously, and so the conduction loss can be reduced. And also, to validate our strategy, we defined a ZVS factor as KD. So KD varies with D. So we plot the KD versus D in this figure. So the Yin equation here defines the ZVS condition. So based on this figure and this ZVS condition, we can well design the parameters to extend the ZVS range. And moreover, due to the existence of the DC blocking capacitor, the proposed topology can effectively block the transformer, effectively avoid the transformer saturation. Here shows the experimental results of this bidirectional converter. So as shown in the steady-state waveforms, using the proposed control strategy, we can realize the transformer voltage matching. So the peak inductor current value is obviously reduced. Meanwhile, by properly designing the parameters, we can realize the ZVS turning on of both primary side switches and the secondary side switches. So the figure to the right shows the measured efficiency data. So we can see that the proposed strategy can realize a 98% peak efficiency. And also the global efficiency is always above 91%, which is good over this wide voltage range. Okay, finally, let me try to make a conclusion to today's webinar. So there are some take-home notes. I hope that you can try to think about it. So first, we are witnessing the paradigm shift from the internal combustion engine vehicle to the plug-in electrical vehicles. This paradigm shift will bring tremendous opportunities to the power electronics industry. However, the charging is one of the most important barriers to driving electric. So how to optimize the design of PEV charging over the wide voltage and load range is the critical challenge. For unidirectional conductive charging, LLC and its derivative topologies are still the dominant topology. And for bidirectional charging technology, dual active bridge and its derivative topology are the mainstream topology. And there are many research opportunities to be explored in advanced topologies, the control strategies, integrated architectures, magnetic integration, as well as the applications of wide bandgap devices. So that's today's talk. So I'd like to acknowledge our sponsors and also my students and my collaborators. Thank you all. Thank you all for listening. I will be glad to take any questions.